Welcome to this lecture about thermodynamics. We have one participant on distance here, Emil. And Emil, if you hear me, you can write something in the chat, like maybe hi or something. Yeah, Emil is hearing me. This is the last lecture before the Jeopardy in the course, and we will discuss thermodynamics. And you see here the points that we should discuss here: state variables and functions, the first law of thermodynamics, reversible and irreversible processes, second law of thermodynamics, entropy and the Clausius inequality, maximum entropy at thermodynamic equilibrium, Clausius-Duhem inequality, thermodynamic framework for constitutive modeling, and thermoplasticity. In thermoplasticity you get also thermal strains because of the change in temperature can give you strains. If we look at this part of the course in your course book here, we can see that everything begins at chapter 20 with basic principles of thermodynamics. So you have to read through chapter 20 here in order to understand thermodynamics if you haven't taken any course on higher level in thermodynamics. And the most important thing in this lecture here is thermodynamic framework for constitutive modeling. And to understand that, you have to read through chapter 20. And after that, we at chapter 21, we have this thermodynamic framework for constitutive modeling. And in chapter 22, we are actually discussing different constitutive models based on the thermodynamical framework. And in chapter 23, we have thermoplasticity. So it's quite much chapters, and the content is quite demanding, I would like to say. So what I have done this lecture here is that I will give you some kind of background in thermodynamics. So I will start with quite simple things, but then I will do a big jump to deriving constitutive models based on the framework of thermodynamics. I think it could be given a whole course about this with 10 lectures. So I have tried my best to make it understandable, this one, but I have made a jump, and you have to read all these chapters to be able to understand everything in detail, I think. So that is, but we will, all these points here is important in this lecture also. Okay, thermodynamics deals with the relations between heat and mechanical work, and it is based on two fundamental laws of nature, the first and second law of thermodynamics. And these two laws, the first and the second law of thermodynamics, are so fundamental that more or less everybody believes that they are true. So it's not something that we should violate when we develop our own constitutive models, because it could be very hard to argue that these laws are wrong in any way. And if we take an easy example, for instance, if I have a glass of water, I have a glass of water in my hand, and the water has a certain temperature, and then I put a fire under the glass of water, then it will be a heat flow to the water, and the water will increase in temperature. Everybody agrees with that. So, but I can also do like this, that I take this glass, the same glass of water, or a identical glass of water, and then I take a pen or something that is like a propeller, and I steer around in the glass of water, or rotate the pen with the propeller down, and it will also increase the temperature of the water because of friction and inside the water. So I can, both by putting the glass of water over a small fire, or put some kind of propeller that I rotate in the glass of water, increase the temperature. And after these two experiments, we have just increased the temperature in the glass of water, and we can't really, it doesn't matter how we have done it. So in that sense, we can say that heat and mechanical work are pretty much two different ways of obtaining the same thing here. So heat and mechanical work are the same thing, in fact, energy. So both heat and mechanical work is energy, and we can, by this experiment with a glass of water, look how these energies are related to each other. And thermodynamics deals then with the relations between heat and mechanical work, and they are based on these two fundamental laws of nature, the first and second law of thermodynamics. Heat is then when we have a heat flow and heating up things. Mechanical work we get when we get displacement of forces. Force times the displacement is an energy, and that is a mechanical work. And then we can look at these two laws of thermodynamics. The first law here is stating that the energy of the universe is always constant. The first law is just conservation of energy. And this first law is important because it also says that a perpetual motion is impossible. So this, what we were discussing last lecture about this kind of machine that was perpetual machine, was not possible. Evighetsmaskin in Swedish. That is not possible. So in the first law, we just have control of the energies and see that they same up. So we have conservation of energy. The second law is a little bit more tricky. The second law can be stated in many different ways, and one of them are this here. The entropy of the universe is always increasing, and that might sound good. I think you have heard it before. But the second law stated like this doesn't say anything about what entropy is. It just say that it's increasing. So we also have to define what the entropy is, and I have taken this definition here. The entropy of a system is defined this way, and in A, if heat delta Q is added reversible to a system at the temperature T, the increase in entropy of the system is delta S, that stands for an increase in entropy, equal to the heat delta Q divided by T here. So we can see that the entropy has the unit joules per degree temperature, joule per degree temperature, and the entropy is a state function also. It says something about the state of the matter. And in B here we can see how the state starts here. We are stating that at the absolute temperature 0, then the entropy is 0, and this is also called the third law of thermodynamics. And maybe you remember from physics that we can see heat as caused by the vibration of the molecules or the atoms in the matter. The more the molecules or the atoms vibrate, the higher the temperature will be. And maybe they are vibrating so much that they are shaking loose from each other, and that is what happens when things are melting, for instance. But we have an absolute 0 point where the molecules and the atoms are not vibrating anymore, and we can't get it any colder than that. And that absolute temperature is minus 273 degrees Celsius, and it's 0 in the Kelvin scale. And at this absolute 0 point, we say that the entropy is 0. So what is important then with entropy here? Well, it tells us what is possible and what is not possible. In a reversible change, the total entropy of all parts of the system, including reservoirs, that say the surrounding, does not change. But in an irreversible change, the total entropy of the system always increases. And the definition of a reversible change is that we could go back to the initial state that we have. Then everything is reversible. We go back to the initial state without influencing the surrounding, then we have a reversible process. But there are no such thing as reversible processes. They are not existing. All the processes are irreversible, and therefore the entropy of the system will always increasing. But it's interesting from a theoretical point of view, reversible processes, because then we can look them as idealizations of certain processes. So the entropy, that is a state parameter, it's very important that state parameter tells us what is possible and not possible, and it has the unit energy per degree temperature. And there are also other ways of stating the second law that comes from the second law. If I, for instance, say that it is possible to convert mechanical energy into heat, but it's not possible to convert heat completely into mechanical energy. So it's possible to completely convert mechanical energy into heat, but the other way around, completely convert heat into mechanical energy is not possible. For instance, this glass of water where we stirred with something with a propeller, that then we convert all the mechanical energy into heat. But the other way around is not possible. And that is also a statement of the second law of thermodynamics. Something so easy as that heat can just flow from a warmer body onto a colder body, not the other way around. Heat can't flow from a cold body to a warm body. That we know. And that is also a consequence of the second law of thermodynamics. Not the first law. The first law just sum up all the energies so they are conserved. But the second law tells us what is possible and not possible in thermodynamics. And it is really a need for some kind of state function that tells us this. And we can't use heat or mechanical work as state functions because they are not. We need some kind of measure like the entropy to say what is possible and not possible. Any comment about entropy? Why can't we have a totally reversible process? Yeah, one say here because of friction. Friction is a very good thing, a very good example of why we have irreversible processes. So friction, for instance. Okay, then I go on here. What? Elastic. They are not reversible, no. You have some heat and because of friction in that kind of process. No process is totally reversible. And it turns out to be possible to derive constitutive theories from thermodynamics, and that's why it's important in this course here that we should study how we derive constitutive theories from thermodynamics. It's a lot of text here, but I think it's important. Most of the constitutive theories discussed previously in the course can also be derived from thermodynamical principles. Thermodynamics opens for a completely new approach to derive other and more advanced constitutive theories. Without the thermodynamic basis, some more advanced models are rather difficult to establish, but with the thermodynamic formulation, the establishment turns out to be pretty straightforward. So, for instance, models that are dealing with plasticity and damage at the same time, you could derive from thermodynamics, and it's not so easy other way. And of course, the good thing here is that we will satisfy the first and the second law of thermodynamics if we derive constitutive models from the thermodynamics principles. If our suggestions for a constitutive model satisfy the second law, all formal physical requirements are fulfilled. That's the law with the entropy. Whether the suggested models provide a close approximation to the actual behavior of the materials in question is another issue where thermodynamics cannot give any help. And then we can raise the question, how should we do as scientists if we are developing our own constitutive models? What is important here? One argue is that we should always develop models that are fulfilling the physical laws, and the reason for that is that if we use the constitutive model in the finite element method, if we not fulfill all these important physical laws, like the second law of thermodynamics, some strange thing can happen in the finite element method if we use such a constitutive model that is not satisfying physical laws. And it could be very hard for a user to understand all this theory, to be able to understand when bad things happen in the finite element method and so on. That is one argument. So some researchers say that it doesn't matter if the constitutive model is good to simulate the material. The first thing that should be solved is that it's okay from a thermodynamical point of view. Then the next step is that to try to make the model simulate actual material behavior. Other kind of argument could be that, well, we understand that we are not modeling the exact behavior. We have just models of the physical world, and we make these constitutive models as good as possible to simulate real material behavior. And because of that, we don't need to satisfy the physical laws. It's not so important because we just have a model of the reality. It's not the reality itself. And what do you think about this? What is important and what is not important when you develop constitutive models? No. The answer is, Roger say that it depends on what you use the models for. Maybe you don't need a perfect model all the time with a satisfied thermodynamical principles. But if we have the constitutive model in a commercial software, that is really. And we know that we have users in commercial softwares that don't understand so very much. In fact, it's just to look at how much you understand in this course. No one reads on a higher level than you. It's also difficult for us, this subject. So how is it for some user of finite element methods? So I think it's something that is worth to think about this, what we really want with constitutive modeling and how we protect users that don't understand enough so for getting totally wrong results without noting it. But a good start would be to satisfy this physical principle, the second law of thermodynamics, and hopefully also get a model that is good to model the actual behavior of the material. Yes. Yes, I agree that, of course, thermodynamics doesn't guarantee that it's a good constitutive model to model the material behavior, but it guarantees that it's not violating the very important physical principle of the second law of thermodynamics. And if you have a model that violates important physical principles, it could happen strange things in the simulation, depending on what you're trying to simulate. I know that if you have a constitutive model that is not okay from a physical point of view, then it can be wrong if you run it in such a way that so the model is not perfect, because you can, for instance, win or lose energy and so on. You can do things that are not physical possible with the constitutive model. But you can anyway have a model that is good to simulate material behavior for a certain experiment that you calibrate the model to. But it's a danger, because you can just calibrate against certain experimental tests, and you don't know what happens for other tests. And if you have violated physical principles, the model is not perfect. It could happen strange things. And then if it's in a commercial program and you have a user that don't understand this, which most users don't understand, then it could be a little bit dangerous. Yeah. That's what this lecture is about, how we derive constitutive models from thermodynamical principles. So let's see how we do. The first law places no restrictions on constitutive modeling, but it determines the temperature distribution. So it's the second law of thermodynamics that should be fulfilled in constitutive modeling. But we get the heat capacity, heat flow equation from first law, and we get the temperature distribution. Okay, then I have jumped now a little bit in the book here. Here we have some fundamental equations, and they are based on the first and the second law of thermodynamics. And it's really these two first equations here. Here we have the Helmholtz free energy state function, and the Helmholtz free energy state function is a function of the absolute temperature in a Kelvin scale, the elastic strains, that we see the elastic strain tensor here, that's the difference between the total strains minus the plastic strains, and some internal variables, kappa, alpha. It could be several this kind of internal variables. And we also have mechanical dissipation inequality that also comes from the second law of thermodynamics. And the mechanical dissipation inequality are defined as the stress tensor times the increment of a plastic strain tensor. See, dummy indexes, so it's contraction here, minus the conjugated thermodynamic forces. That is really what we call for hardening parameters before in the plasticity theory, times increments in these internal variables. And this mechanical dissipation energy should be larger or equal to 0. In fact, if we have elastic unloading, it will be equal to 0 here. And we see that we have these relations here, that the stress tensor is equal to the mass density times the partial derivative of the Helmholtz free energy function with respect to the strains. And then in this relation here we see that the stresses are energy conjugated to the strains here. And below here we have this K alpha, that is what we have looked at before as the hardening parameters, and this is defined as the mass density times the partial derivative of Helmholtz free energy function with respect to the internal variables. So we can see that these Harding parameters K are energy conjugated to the internal variables here, and that's why we have this name for K alpha here, conjugated thermodynamic forces, because it's energy conjugated in the same way as the stress to the strain here. And of course, now I don't give the background to how we have got these equations here, but it stands in the book. It's much derivations to come to this Helmholtz free energy function and the mechanical dissipation inequality, but they are based on the first and the second law of thermodynamics. That is what is the information here, and they are just formulated in such a way that it's good for deriving constitutive models here in plasticity. So we start from here to just understand that there are this first and the second law here in this. That's nothing else. It's just structured in such a way. We have need a yield function, and it's quite obvious that the yield function should be a function of the stress tensor, but since in these equations here that the stress tensor or energy conjugate to the strain tensor, and we also have this conjugated thermodynamic forces that are energy conjugated to the internal variables, then it's logical also to put the conjugated thermodynamic forces as parameters in the yield function. And the yield function should be smaller or equal to 0 as we limit between elastic and plastic deformations. Okay. Now we should we haven't said anything about the Helmholtz free energy function. We have just say what its function, what kind of variables we have in this function here. So we need also an actual function. And if we are disregarding thermoplasticity, that is strains, thermostrains, strains that comes from the temperature, a natural choice of the Helmholtz free energy function for plasticity is this one. We just multiply the Helmholtz free energy function with the mass density here. And we have three different terms here that is not coupled to each other. The mass density times an arbitrary function of the temperature here, plus 1.5 this elastic strains times the elastic stiffness tensor times the elastic strain tensor here. And you see that it's we have contraction of this parameters here. So it's we get a scalar in the end, plus mass density times an arbitrary function of the internal variables kappa alpha. So this Helmholtz function is split into three separate parts, and no coupling effects are presented between the three sets of variables. And in fact, the background to why choosing like this is based on thermoelasticity that is described in the book. So this function here are taken similar to the thermoelastic theory. We see that we have these properties here, sigma EE and K alpha here, and now we have a function here, so we can take these partial derivatives and we get these results here. If we take this partial derivative here, we get this result. And then you can see that these results are Hooke's law. It's nothing else than Hooke's law. You see it? Yeah. So by using this thermodynamical framework, we end up with Hooke's law here for this partial derivative here. And the partial derivative for these hardening parameters, we get like this here. We come back to it later. But we get very soon a very important result, Hooke's law here, out from thermodynamical principles. Isn't it fantastic? That you can go around and tell people the whole day, hey, do you know? The next step is evolution laws for the fluxes here. We have an increment of the plastic strain tensor and an increment of the internal variables here. And the only formal requirement is that these evolution laws must be such that the dissipation inequality is fulfilled. The dissipation inequality must be fulfilled. And the dissipation inequality we have here, mechanical dissipation inequality, like this. And it says it should be larger or equal to 0. Well, what should we do then? It's okay as long as we fulfill this inequality, larger or equal to 0. And we have here a postulate of maximum dissipation. For instance, if we want to have as large dissipation as possible, then for a given fluxes of this and this, find those stresses sigma EE and conjugated forces that minimize this dissipation inequality under the constraint that the yield function should be smaller or equal to 0. In optimization literature, we are minimizing things. What we want here is to maximize the mechanical dissipation inequality. We want to have it as large as possible. But in mathematics, we deal with minimization problems, and therefore, instead of maximizing this mechanical dissipation, we are minimizing minus the mechanical dissipation. It's just a trick to use minimization method. The yield function f is assumed to be a convex function in sigma EE and the hardening parameters. And you, in fact, by now you understand that the yield function must be convex, otherwise it wouldn't work. How do we calculate something like this kind of optimization problem here? Do you know the name of the mathematics we can use to solve this problem? You have everybody have probably read it in mathematics. You remember Lagrange multipliers. That is what we can use for this minimization problem here, because we have a constraint here. You remember that Lagrange multipliers we could use when we have constraints, and our constraint here is that the yield function should be smaller or equal to 0 here. So we use Lagrange multipliers. And in Lagrange multipliers, we maybe remember that first we have this function that we should minimize here, plus a Lagrange multiplier, let's call it lambda dot like this, multiplied with the constraint F, that is the yield function here. That is Lagrange multiplier. So the Lagrange multiplier here is a function of the stress tensor, the hardening parameters, and this Lagrange multiplier lambda dot, like this. And it looks like this if we write out this Lagrange function that we should use for minimization this problem with a constraint. And the active constraint f equal to 0 gives, we take the partial derivative of this Lagrange function with respect of the stresses, and then we get this result here. Just derivate this with respect to the stresses, and you see you end up with this result here, because you have stresses both in this term and this term here, so you end up with this result here, and that should be equal to 0 according to this Lagrange mathematics. And we take the partial derivative of this Lagrange function with respect to the hardening parameters, and then we get this result here, hardening parameter both in this term and this term here, and that should be equal to 0 according to this mathematics. So this first partial derivative of the Lagrangian function gives us this result here, and this result here you by now recognize as the flow rule for associated flow. So by taking maximizing the dissipation inequality, we get the associated flow rule from this. The associated flow rule. And this other relation here, we get this result here that we will come back to later on. But we will also get the Contactor relations here from this Lagrange mathematics, because we also get that this Lagrange multiplier times the yield function should be equal to 0 here. So we get by this also the loading conditions in plasticity. If and since we have this in the flow rule, we have this Lagrange multiplier here as our plastic multiplier in the flow rule, so that's why it becomes, the Lagrange multiplier becomes the plastic multiplier. And this holds here, and then then we can get this result here, that when the yield function is 0, then the plastic multiplier must be larger or equal to 0, and if the yield function value is smaller than 0, then the Lagrange multiplier must be equal to 0. So it's quite much things we get from this that we already know from plasticity earlier. And this is from the laws of thermodynamics. We get this. We can also establish these fluxes here by using a dissipation function that looks like this, and you can read yourself about it in the course book on these pages here. The only important thing is that we do in a little bit different way, and then the result is giving the non-associated evaluation equations. So here we see the flow rule for non-associated plasticity, and that we get from this theory here, also based on thermodynamics. And this expression here, depending on the potential function instead of the yield function, as we have in associated plasticity. Everybody follow so far? Easy? But I think we take a 5 minutes break here. 5 minutes break. And we should continue again. So, Emil, if you move to your computer here, and everybody in the room here in Luleå, move to their places. We get this relation here that the Lagrange multiplier, or the plastic multiplier as we know it, times the yield function should be equal to 0 from this optimization method with Lagrange here. And if we are differentiating this relation here, you know, when we take the derivative of a product, then we take the derivative of lambda and holding f constant, and then plus holding lambda dot constant and taking the derivative of f. And then we get this result here. And for plastic loading, f must be equal to 0, which implies that then this is equal to 0. And for lambda larger than 0, then f dot should be equal to 0. So here we have, in fact, the consistency condition from thermodynamics then, and the consistency condition is stating that the stress point should be situated on the yield surface during plastic loading. So we also got these results from the laws of thermodynamics by this. We continue here with the consistency condition. If we take f dot from this yield function here, we should see what happened with the yield function value if we have small changes in the parameters, variables of the yield function here. F dot should be equal to 0 in plastic loading. Def the sigma E dot, an increment of stress tensor, plus def the K alpha, the hardening parameters, times increments in hardening parameters. And everything should be 0 if the stress point is situated on the yield locus during plastic loading. We have these results from the derivatives before. This result here we got from the Helmholtz free energy function when we take this derivative here, those derivatives here. We have this result here. And then we have this function here. And if we differentiate this function here also, we get this result here. The second derivative here. Notice how I need to do with the indexes in the tensor notation here. I must put this beta as a dummy index here to get this sum correct. I can never have more than 2 indexes of the same kind in tensor mathematics, and sometimes it could be a little bit tricky to write this equation. And this result here, and if I take this result here comes from the Lagrange multiplier technique here, the Lagrange here, this result. And I substitute this result into this equation here, and I get this result here. And then I substitute this result here into the K dot alpha in the consistency relation here. And the consistency relation will be like this here. And then we can make a substitution for everything that stands here, everything that stands together with the plastic multiplier here, we are calling for H here. So it's just substitution, and we see that H will be this here, the stuff together with lambda dot in this term here. And then we have again the generalized plastic modulus from plasticity theory, based then on thermodynamics from the beginning. So you see how step by step all the important information in plasticity comes out from the thermodynamical principles here. And then we are quite home here. We have the general format of the constitutive equations. We have the Hooke's law here. And if I write this equation like this here, I can substitute with the flow rule here. And then it becomes like this. And then this result here comes from the page before. I take this equation here in the consistency condition and reformulate it like this here. And then for the increments in the stress tensor, I substitute with this here, and I get this information. And then I multiply this factor into the terms here. I get this result. Then I make a move this term to the left side and make a factorization. So I get the plastic multiplier here. And then I solve for the plastic multiplier, substituting everything here as big A. And then it's just like this, and we can see also that A should be larger than 0. And this is the result that we have already derived before in plasticity. And then I can go to this Hooke's law here, and substitute for lambda dot, this information here, and I get this result. And you see once again that it's a lot of dummy indexes here, MN, ST, and I can just have 2 index of the same type, of course, in tensor mathematics. I make a factorization, so I get the strain increments on this side here, and I can solve for the elastoplastic stiffness matrix here, like this, and we see that it's exactly the same results as we have seen before in plasticity. So all fundamental equations of general plasticity have been rederived in a fashion that fulfill all formal thermodynamical requirements. The choice of the function for the internal variables in the dissipation, in the Helmholtz free energy function, and the internal variables remain. We haven't solved for those yet. But then we can draw the conclusion that this kind of the plasticity derived like this is fulfilling thermodynamical requirements so far. To get these internal variables, we have to specify on some constitutive models, and we once again go to the isotropic hardening von Mises model with associated plasticity. Just as an example, you can choose other models to try this out. And in the von Mises model, we have this yield function, the effective stress, that's like this, minus sigma y, that is like this, and then it becomes minus sigma y 0, the initial stress, minus the hardening parameter, big K. We take the evolution laws for associated plasticity here, and we see that it will be like this. Then we can define the effective incremental plastic strain like this here, and we see by substitution of the flow rule here, we get this result here, and this result, and this result, and everything goes away, so we are just left with the plastic multiplier. So the effective strain, the effective incremental plastic strain is equal to the plastic multiplier, and then it's we can see that this internal variable is equal to this result here that we got from the Lagrange multipliers here. This result here we use once again here for the von Mises model. And if we take the partial derivative of the yield function with respect to the hardening parameter here, we see that this is just -1. So the internal variable is equal to the plastic multiplier, that's equal to the effective plastic strain increment. And then the effective plastic strain emerges as a natural internal variable for isotropic von Mises plasticity as a consequence of the thermodynamical formulation. We have, in fact, proved that also here. And then we go to the generalized plastic modulus here. We have this result here. The F decay is just -1, -1 times -1 is 1, so we are left with this result here. This we got from the derivatives of the Helmholtz function in the beginning. Here, this result. But then, of course, we have put in these 3 terms in the Helmholtz function, so it becomes this term here. We have like this, because internal variable is equal to the effective plastic strain, and the K is equal to the sigma y that we see here, because the sigma y 0 is the initial stress and it's fixed, so a change in sigma y is equal to a change in the hardening parameter. So we have this result here. Exactly the same result as when we derived the isotropic von Mises model, the first lecture I had in the course. And then we can have different type of hardening of this von Mises model. If we, for instance, say that this hardening is linear, then sigma y is equal to sigma y 0 plus some linear hardening, the hardening modulus times the effective plastic strain here. You see then that K will be the effective plastic strain, because sigma y is sigma y 0 plus K here. And then if we make an integration of this result here, we just integrate it, then we get this result here. We see that when we integrate this side here, then we get on this side, we get it up to 2 here, the effective plastic strain, and divided by 1 divided by 2 here. It's just integration of the polynomial, of course. So then we get this function here in Helmholtz function from the beginning. In the Helmholtz function, we had chosen this third term here, and in this third term, we have this function here, and by assuming linear hardening, that function will be like this here. And if we, for instance, assume Power law hardening, then such a hardening could be like this. And then our hardening parameter will be like this. And if we integrate this here, it's just another polynomial, then we get this result here. And then our function in the Helmholtz function will be like this for Power law hardening. And if we, for instance, assume exponential hardening, then we have this function for exponential hardening. The hardening parameter will be like this. We make an integration, and we see that this third term in the Helmholtz function will be like this for exponential hardening. This last step here is very important here. We go back to the mechanical dissipation inequality, and this mechanical dissipation inequality must be larger or equal to 0. And the question is, will it always be larger or equal to 0? Because that is very important here. Otherwise, the second law is not fulfilled. And then we have the mechanical dissipation inequality here, and for the plastic incremental strain tensor, we substitute with the flow rule, and for Mises model, we have the partial derivative in the flow rule here that we substitute with also, and we just have one hardening parameter in for Mises, that is K. And our internal variable is equal to the plastic multiplier for Mises. So it's like this. So I make a factorization and take the plastic multiplier outside this parenthesis here. And then I multiply sigma EE with SCE here. And then that is the same as multiply SCE with SCE. Do you know why? You see that this becomes the same as this. Because SCE is equal to sigma IE minus 1/3 of the sigma KK times the Kronecker delta. And then you will see that by putting up that equation, you will see that you end up with this result here, because the first invariant of the deviatoric stress tensor is SCE is equal to 0. You can try it yourself. It's a good practice. Comes to here, and then we see that it will just be this result left here, but this is equal to sigma y0, and the plastic multiplier must also always be equal, larger or equal to 0, and of course the initial stress here should be positive in this sense. So the mechanical dissipation inequality is always larger or equal to 0. This is fulfilled irrespective of the hardening chosen. It doesn't matter of the hardening we choose. The mechanical dissipation inequality is always fulfilled for isotropic von Mises model. Okay, I think that the things that I have discussed today is quite demanding. It's not easy at all. This lecture and also the chapters in the book are a little bit demanding, but I think that this is anyway extremely important to teach this part of plasticity. And the most important thing you learn today, hopefully, is that you can derive plasticity models from thermodynamics. It is possible. And then, if you as a researcher want to develop your own constitutive models, it's important that you understand that you should probably check if the second law of thermodynamics is fulfilled or not if you try to develop models. Otherwise, if some reviewer will ask you that question. It is, of course, important that we try to make constitutive models that are based on physical principles, and this second law of thermodynamics is one law that we believe is true, and it's not probably something that we should violate. And so if you, I don't think it's possible to understand all things I say in such a lecture just by sitting here and listening to me, but the important stuff is that you can develop constitutive models from thermodynamics, and you should probably look at that aspect if you are developing your own constitutive models, whatever kind of constitutive models you are developing. And then, if you do that, you can learn all this theory behind it. Just take time, I think, maybe several days or weeks to learn all this. But it's worth it if you will work with it. For other course participants, you know now that this is something that is possible, and that is well with that. And if you're interested, you can read the chapters in the book. It's funny with the mathematics anyway, don't you think? Yeah. But it's quite demanding, and probably we also need some kind of higher level course in thermodynamics on PhD level or something like that to understand this material completely. But I think it's so important. That's why I give this lecture every time we have this course. I know about cases where people have done very good constitutive models, but they are not fulfilling the second law of thermodynamics. And that is a big drawback, and it's a little bit sorry for those that spend a lot of effort developing models, if they don't know about these things that the second law of thermodynamics should be probably fulfilled, and it's possible to go out from thermodynamical principle and derive constitutive models. So that's what I want to obtain with this lecture here. But I know that it's demanding, so if you feel that this was difficult, you should understand that it's difficult for me too. Yeah. Any questions? Okay, thank you for today. And thank you, Emil.